we're going to continue to work with differential equations. Now we're going to introduce a new kind of differential equation. We have been working with equations of the form dy over dx equals f of x y, where the function f of x y was special enough that it could be separated into the product of a function of x and a function of y, so that we could use separation of variables to solve the differential equation. However, that's not always possible. It's not always the case that f is the product of two different functions, one of x and one of y. Sometimes it's possible, though, to express the function f as a function of a new variable that we're going to call v that is defined as y over x. So if we're lucky enough that our function can be expressed as a function of that new variable v, f of y over x, then we call this kind of equation, we call it a homogeneous differential equation. Let me give you two examples of these kind of equations. The first one would be dy over dx equals y squared over x squared. The function that I have in the right hand side can be expressed in the form y over x squared, making it a homogeneous differential equation. Now a second example is going to be this function, dy over dx equals x squared plus y squared over 2xy. Unlike the first example, this one is not as evident. That is going to be a homogeneous equation. This equation will require a little bit of algebra manipulation to see that it actually can be written in the form f of y over x. So when you're presented with a differential equation, you first need to try manipulate the equation that you have and see if you can make it into the form of a function in terms of y over x. So let me show you in this example how that would work. So I can separate this sum as x squared over 2xy plus y squared over 2xy. And then one of these x's cancels and this y cancels with one of these y's. My function becomes x over 2y plus y over 2x. We can see that the second term is already in the form y over x. Now the first term, what I need to do is I need to move this x that is in the numerator. I'm going to bring it to the denominator of the denominator. So I'm going to build a fraction in the denominator that has a numerator equal to y and a denominator equal to x. So this would be 1 over 2 times 1 over y over x. And now the function f of xy has been written in terms of y over x. What is the general idea behind homogeneous differential equations? The main idea is that we are defining the variable v as y over x, which means our variable y can be expressed as the variable v times x. Now this gives me a tool to transform the original equation into another equation in terms of v and of x. In general, the process is going to be as follows. We're going to substitute y over x into our function f of xy. So our differential equation becomes dy over dx equals f of v. Now the left-hand side, we can recalculate it if we substitute y with vx. Then we can treat this derivative as a product of the function v and the function x, and we can take the derivative using the product rule, and that is going to be x dv over dx plus v times dx over dx. Now the x over dx is 1, so this expression is x dv over dx plus v. And then when I substitute 1 into the original differential equation, I'm going to get x dv dx plus v is equal to f of v. Now, what is good about this new differential equation is that this equation is separable and can be solved using the method of separation of variables. Let me show you in general how that's going to work. We have the new equation x dv dx plus v equals to f of v. We're going to start by moving the plus v from the left hand side and towards the right hand side to f of v minus v. Now we want to move everything that has v to the left hand side and everything that has x to the right hand side. So this is equal to 1 over f of v minus v dv equals 1 over x dx, which means from this point onwards we can simply integrate to solve the differential equation. Once the equation is solved, we can use the substitution to go back to the original function y. Let's take a look at a few examples to see this method in action. Find the general solution of dy over dx equals x squared plus y squared over 2xy, where x and y are bigger than 0 in the form y squared equals f of x. So the first thing that we notice is that this is the same differential equation that we just talked about. So we are familiar already with this function and we know how to turn it into a function of the form f of y over x. So let's repeat that process again. So we wanted to separate the fractions and we wanted to simplify to get x over 2y plus y over 2x, and then we just write it in the form, and then we just write it in terms of y over x like so. Y over x plus 1/2 y over x. So like I said before, we are going to do the substitution. V is going to be y over x. So my differential equation for now is going to look like this. 1 over 2v plus 1 over 2v. Now I need to deal with the left hand side. So the process that I'm going to do in the left hand side is standard. It is exactly the same thing I just showed you. So dy over dx is going to be d dx of vx, and that we saw was equal to x dv dx plus v. So I'm not going to do this process all the time with as much detail as before. I'm just going to go ahead and substitute it into my equation so that this gets x dv dx plus v is equal to 1 over 2v plus 1/2 of v. Now, as you can see, this function is separable, so we're going to separate we're going to use the method of separation of variables to solve this equation. So first, we are going to move that plus b to the other side. So 1 over 2v plus 1/2 of b minus v would be minus 1/2 of b. And now what I want to do is I want to divide 1 over 2v minus 1/2 of v dv equals 1 over x dx. I'm going to try to move things around in the left hand side to simplify that expression or make it into a more comfortable expression. And now we can integrate on both sides. I just cleaned up the space a little bit, but here we have the integrals that we had before. So we're going to do the integral to the left hand side using a short substitution. That is going to lead to the solution minus ln of absolute value 1 minus v squared. And then the right hand side is simply ln x plus the constant of integration. Then what we want to do now is to solve for v squared. So what we're going to do is we are going to multiply everything by minus 1, ln of 1 minus v squared equals minus ln x minus c. And we're going to do everything as exponent of e. So e to the power of the expression that we have, e to the power of this, e to the power of this. So the exponential and the natural logarithm would cancel out, and we just get on the left hand side 1 minus v squared, and on the right hand side we can separate this exponential into two exponentials. One is e to the power of minus ln x times e to the power of minus c. Now the first one, the first exponential, can be simplified and we just get 1 over x. And we can rename this constant e power minus c as a new constant a. So the right hand side just becomes a over x. And we can solve for v squared. 1 minus a over x would be equal to v squared. And if we substitute v squared with y over x, this is y squared over x squared, which means that solving for y, x squared minus ax is equal to y squared. Or if you prefer, y squared is equal to x minus a. Let's do a second example. Show that the substitution x equals capital X minus 1 and y equals capital Y plus 3 turns the differential equation that we see here into a homogeneous differential equation. Also, hence, find the particular solution with x equals 0, y equals 3, giving your answer in the form f of x, y equals to c. So we're going to start with part A, and we need to do the substitution that they are suggesting. So for x, dx is going to be the same as d capital X, and dy is going to be the same as d capital Y. Therefore, we can substitute dy over dx as d capital Y over dx in capital. Then the right hand side is going to become 4x minus 1 minus y plus 3 plus 7 over 2x minus 1 plus y plus 3 minus 1. Let's simplify that, and we get 4x minus 4 minus y minus 3 plus 7 over 2x minus 2 plus y plus 3 minus 1. Simplifying, 4x minus y over 2x plus y. So now if we want to show that this is a homogeneous differential equation, we have to substitute the variable v equals y over x. That means we need to show that the right hand side can be written as a function of y over x, and that is achieved by dividing everything top and bottom by x. So our differential equation is going to look like dy over dx is equal to 4 minus y over x over 2 plus y over x. So we can say here, thus, the differential equation is homogeneous. Now, in order to solve the differential equation, we need to complete the substitution. So with the substitution v equals y over x, then we get y equals vx, and that means the derivative of y with respect to x is going to be v plus x dv dx. And substituting that in the left hand side and v in the right hand side, we get v plus x dv dx is equal to 4 minus v over 2 plus v. Now this is the differential equation that we're going to solve by separation of variables. So let's clean the part A so that we can get working on the solution. Now, to solve this by separation of variables, what we want to do is move everything that has b to one side. So I'm going to start by moving this v to the right hand side. X dv over dx is equal to 4 minus v over 2 plus v minus v. Let's try to simplify this. And now we're going to move everything that has b to the left and everything that has x to the right. So this would be 2 plus v over v squared plus 3v minus 4 dv equals 1 over x dx. Now we proceed to integrate. So the integral of 2 plus v over v squared plus 3v minus 4 dv would be the integral of 1 over x dx. To do the integral on the left hand side, I'm going to use the method of partial fractions. So to start the process of partial fractions, I want to write 2 plus v over v squared plus 3v minus 4 in factorized form, and that is v plus 4 times v minus 1. So the partial fractions would be a over v plus 4 plus b over v minus 1. Now I want to find the values of a and b so that I can separate this big fraction into the two smaller ones. So let's do this process really quickly and we will come back to the integral. Now substituting these fractions into the integral, like so, and then we can separate this integral into two smaller integrals, like this. So 2 minus 2/5 integral 1 over v plus 4 dv minus 3/5 integral of 1 over v minus 1 dv equals to the integral of 1 over x dx. And now we proceed to integrate. So the first integral is minus 2/5 ln of absolute value of b plus 4. The second one is minus 3/5 ln of v minus 1. And then ln of absolute value of x plus c. Now I'm going to use the properties of the logarithms to write this expression in a more simplified way. And now we're going to use the initial condition to find the value of c. When x is 0, y is 3 means for small x to be 0, big X minus 1 is going to be 0. That means big X is equal to 1. And for y equals 3, that means big Y plus 3 has to be 3. That means big Y is equal to 0. Then if this is the case, then the variable v is going to be 0 when x is equal to 0. So the substitution becomes ln absolute value of 4 to the power of minus 2/5 over 1 times 0 minus 1 to the power of 3/5 is equal to c. This is ln of, so this is minus 1 over 4 to the power of 2/5. Thus, we can go back and substitute into our expression for the solution. So that is ln of absolute value of v plus 4 to the power of minus 2/5 over x times v minus 1 to the power of 3/5 absolute value equals to minus 2/5 ln of 4. Now, to finish the problem, we have to go back to the original variables small x and y. So I'm going to substitute back the value of v in terms of the lowercase x and the lowercase y. So now we got a simpler expression for the logarithm in terms of the original values x and y. Now it's your turn. Here I'm giving you two questions for you to practice the solution of homogeneous differential equations. Please don't forget that you can bring any questions that you have about these two problems or any complications that you encounter in the process of solving these two problems to the class.